Assalamualaikum. I be to the panel and my group mate. Today, we are going to present about the production of methanol. This presentation has been prepared by me, Muhammad Hamizan, Nur Ain Shazwani, Nurul Hasanah, Nurul Liana, and one Nur Fatini.
Assalamualaikum. Hi, I'm Amdurul Hassan Nabitifan and I'm going to talk about the process integration in our plant. First, let's take data. So we are going to get the data from the PFD diagram, and by referring the PFD diagram, we can see that there is one cool stream that has to heat up first before enter the reactor, and another 4 hot stream that have to cooling down. Alright, in the pinch analysis, the first step we have to do is we have to know the value of the minimum temperature difference between the hot and the cool stream for the heat recovery. And we determine that for our plant, we are using the 15 degrees Celsius, which is the range between the 10 until 20 degrees Celsius for the petrochemical plants. And then we take a look to the composite curve here. This is our composite curve diagram in our plants, and we determine that we are facing the threshold problem where we are not required any external hot utilities, and we just only have the cooling and external cooling utilities. Okay, from the table of pinch analysis here, it's proof that we are not need any external hot utilities here because the QH mean is 0, and we only need the cooling and external cooling utilities around 15,000 kilowatts. And we determine that the temperature pinch between hot and cool stream is between 360 and then 345 degrees Celsius. Next, for the heat exchanger direct designs, so this is required in order to know how much heat exchanger are needed in our plant, where we have to put the heat exchanger in our streams, and we need to know how much more the utilities that were needed. So, by referring to the figure A, it shows that in our plant we need 1 heat exchanger, and we are still need 4 coolers. If you are referring to the figure A, there is no heat load loop in order to optimize the energy usage. And let's refer to the cooler number 1. The amount of cooler 1 needed is around 10,000 kilowatts. And in reality, this is a huge amount of energy to be cooling down. So we have done some research, and there is the maximum amount energy that can be cooling down for the coolers. It's around 4,600 kilowatts by the Thermac equipments. So by splitting the cooler number 1 into 3 coolers, it can give a high efficiency of cooling down the streams. So by referring to the figure B, it shows that in our plant we need 1 heat exchanger and 6 coolers. Current composite curve. So from the diagram we can see the current composite curve from the shifted temperature converted into the graph, and from the graph we can determine we are using the cooling water and refrigerants. So here is the comparison PFD between the before and after the process integration. After process integration, we can see that there's a lot of saving here. For energy savings, there's no external hot utilities. You can say that 100% saving here for the hot utilities, and there is 29.36% save for cool utilities. And if we refer to the utilities cost, we can save around 85% of it, and it's a huge difference from the original one. So in conclusion, we can say that in our plant there is 1 heat exchanger and 6 coolers, and we'll be able to minimize the utilities cost, reduce the cost of operational plant, and we can say that this process integration can be applied in our plant. Thank you.
So today I'm going to present about process control and instrumentation. So the purpose of the application of process control and instrumentation is to increase the efficiency, durability, safety protection, optimization, and consistency of implementation system. Alright, so to design the process control and instrumentation scheme, there are few primary objectives needed to be considered, such as first, safe planned operation. For a typical chemical process, the process variables such as operating pressure, temperature, concentration of composition should be kept within allowable limits. Alarm and automatic shutdown system should be provided to detect dangerous situation. So next, second is production rate and quality. In methanol plant, the target on the production rate is to be produce 100,000 metric ton per year. Therefore, system is designed to ensure the maximum production of methanol within certain specification. So the third is economic. A plant should operate at the lowest production cost as economic as possible in its utilization of raw material, energy, capital, and human resources. The following guides are used to identify and locate the control instrument in the process. So first, identify and draw in those control loops that are obviously needed for safety for steady plant operation, such as level controls, flow controls, pressure controls, temperature controls, composition controls. Second, identify the key process variable that need to be controlled to achieve the specified product quality includes control loop by using direct measurement of the control variable where possible. So the third is identify and include those additional control loops for safe operation not covered in step 1 and 3. 4. Decide and show those auxiliary instruments needed for monitoring the plant operation by operator, troubleshooting, and plant development. It is well worthwhile including additional connection for instruments that may be needed for future troubleshooting, and developments are not installed permanently. These include pressure tapping orifice and extra sample points. So the fifth is decide on the location of sample points. So the sixth, decide on the need for recorder and location of the readout points, local or control room. This step would be done in conjunction with step 1 to 4. So the seven is decide on the alarms and interlocks needed. This would be done in conjunction with step 3. So this is the example of PNID for reactor, plug flow reactor 100. So this is the example PNID for heat exchanger. So this one is example PNID for separator. So this is the example of PNID distillation column D100. And this one is the example of PNID distillation column D101. So here is the specification sheet for my design reactor. So the identification is multi-tubular reactor. The name is reactor plug flow reactor 100. Function is hydrogenation of carbon dioxide to produce methanol. Specification is design type horizontal. Material of construction is stainless steel 316 because I'm using this because it has a stronger resistance to various chemical agents that might damage or corrode. It can tolerate fatty acid, tartaric acid, and chloride even at high temperature. So next is mass flow rate is 44.6 kg per second. Reactor diameter is 2.46 meter. Reactor length is 9 meter. Reactor volume is 57.03 meter cube. Resident times is 0.6 hour. Dome head type is torus spherical. I'm choosing this because it has the reduction overall lower length compared to that one to the one with hemispherical head. So the thickness head is 4.17 millimeter. Type vessel support is saddle support. So the material of saddle is carbon steel. I'm choosing this because it's durable. Carbon steel is extremely strong and shock resistant. It's safe compared to many other material. This is the view from AutoCAD drawing in cross-sectional view, side cross-sectional area, top view, and front view.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Aisyah Zwani binti Rosni Ibijama. Now I will proceed to another equipment which is heat exchanger. The main objective to design the heat exchanger is to cool down the temperature from 360.8 degrees C to 242.05 degrees C. The product from the heat exchanger need to be cooled down before enter a reactor. Cooling water has been used to cool down the temperature. The table shows the summary for the chemical design. The type of heat exchanger used is shell and tube heat exchanger. This is because the capital cost for this equipment is the lowest. The heat duty for the equipment is 5,881.468 kilowatt. For the tube side fluid, which is hot stream, it's referred to the methanol solution in stream 5 to 6, while for the shell side fluid, which is cool stream, it's referred to the cooling water. The inlet temperature for the hot stream is 360.8 degrees C, while the outlet temperature is 242.05 degrees C. While for the cool stream, the inlet temperature is 25 degrees C, while the outlet temperature is 55 degrees C. The selectivity of the stream is based on the temperature of the fluid. In the table also show the tube side specification where there is 52 number of tube and the type of pitch used is triangular pitch. For the shell side specification, there is 33 number of baffle. Next, the table shows the summary for the mechanical design. The pressure and temperature was obtained from the simulation for the shell and tube side. The material of construction used is carbon steel. This is because it is more stronger and more durable than others, such as stainless steel. Since the pressure is below 15 bar, so the ellipsoidal head has been used as the head because it is more economically for operation below 15 bar. The figure shows the design of heat exchanger. The upper picture shows the design of baffle, while the bottom picture at the left side shows the design of saddle support and nozzle, while the right side shows the design of bundles, tube bundles.
Hi, I'm Hassana. So my equipment design is about a separator for liquid vapor separations. So my separator consists of 2 feed inlets which come from a reactor and are recycled from the distillation column number 1. And then the vapor that separate from the liquid will recycle back to the mixer. Okay, this is how my equipment design looks like. So the vessels in a vertical configurations, and it has the demister pad as mist eliminator. And from the side view, we can see there is 2 inlets of the nozzle, and we have a bottom nozzle of the product, liquid product, and the top bottom nozzle for the vapor product. Okay, and then from the top view, we can see there's a demister inside, and at the view A, it shows that the skirt designs for the support designs of my vessels. And here we can see the height is around 11.83 meters. It's constructed by using the carbon steel and it insulated by using the foam glass. At the same time, the head enclosure, we are using the ellipsoidal type because the thickness of ellipsoidal and the thickness of the vessel is similar. Yeah, that's all. Thank you.
Assalamualaikum and good morning to all panels and my fellow friends. My name is Nurul Binti Rahman. Today I will present about the designation of distillation column 3100. Okay, in our industry, distillation process is one of the crucial process to separate the key components in the mixture due to its different boiling point and their relative volatility. So, distillation process is the most used in the chemical and petroleum industry. When we design the distillation column, there are 2 parts that need to be considered, which is chemical designs and the mechanical designs. So, in our process, distillation column is used in order to separate the product of methanol and the water. There are 5 components which are methanol, water, hydrogens, carbon dioxide, and carbon monoxide. So the first table shows the summarization of chemical design for distillation column T100. From the calculations, the column height obtained is 11.1 meter, and we are using material of stainless steel since stainless steel is high in chromium content, which can prevent from corrosion and staining. Then the number of plates that we are obtained here is 21, and we are using carbon steel as plate material since carbon steel is high in carbon, which can give steel lower melting point, more durability, and good in heat distribution. So the next table shows the summarization of the mechanical design for distillation column T100. Okay, mechanical design is very important in order to determine the design pressure and design temperature that will be used in our distillation column. So the design pressure here is 1760 kilopascal, and the design temperature is 74.48 degrees C. Lastly, the figure shows the design AutoCAD for distillation column of T100. So all the design specifications are stated as in figures shown.
Hi, my name is Wanu Fatini binti Wan Bakri. So I'm going to explain on the fifth equipment in this process, which is distillation column 2 T101. So in this distillation column, process involved is separation of water and methanol. So on the right side is the value that I calculated from my calculation, that I get from my calculation. So the column type that I go for is sieve tray, primarily because the design information for plate column is more readily available compared to pack column. And then pack column generally is for diameter less than 1.5. The diameter that I calculated is 2.3 meters, hence I opt for sieve tray. Plus, a sieve tray handles wide range liquid rates without flooding. And then for column material, I go for carbon steel. This is also primarily because the typical distillation column material used in industry right now is carbon steel. Plus it is more economical, efficient, and then in this process we don't have any process that required special material, hence I go for carbon steel. And then type of head, Torus spherical, insulation material, mineral wool. And then for design support, skirt using carbon steel as well. This is the AutoCAD drawing for distillation column 2 T101 that I've explained all the details in the previous slides. So that is all from me for distillation column 2.
Now, I will proceed with the economic analysis. The table shows the cost of raw material and the catalyst. The cost has been obtained from the metric, and the supplier for the raw material is Linde Sdn Bhd located at Kerteh, Terengganu. Next, the table shows the total cost of the equipment. The equipment that has been used in this plant is mixer, reactor, exchanger, cooler, compressor, separator, splitter, distillation column 1 and distillation column 2. The total cost for the equipment is 41,325,985.77 ringgit Malaysia. Next, the table shows the total manufacturing cost. There are three sections, which is direct manufacturing cost, fixed manufacturing cost, and general expenses. The cost included in the direct manufacturing cost is the raw material, waste treatment, utilities, operating labor, direct supervisory and electrical labor, maintenance and repair, operating supplies, laboratory charge, and patent and royalties. Under the fixed manufacturing cost, there is depreciation cost, local tax and insurance, and plant overhead cost. While under the general expenses, there is administration cost, distribution and selling price, and also the research and development cost. The total overall cost is 426,873,062.2 ringgit Malaysia, while the total cost of manufacturing, which is COM, is 307,691,524.95 ringgit Malaysia. Now, let's talk about the profitability analysis. Profitability analysis is a technique to assess the profitability of the project that involve both capital cost expenditure and yearly operating costs. The graph shows the non-discounted and discounted cash flow diagram. Discounted cash flow, the net present value is 28.87 million ringgit Malaysia, while the cash flow rate of return is 13.3% and the payback period is 10.79 years. While for the non-discounted cash flow, the net present value is 208.02 million and the cash flow rate of return is 13.86%, and also the payback period is 7 years. That's all from me. Thank you.
In ensuring the safety of our plant, there are 4 things that we focus on, which is HIRAC, HAZOP, plant layout, and ERP. So HIRAC stands for hazard identification. It is when we recognize a thing that can cause harm or injury. And then we go for risk assessment, where we look at the possibility of those injuries happen to a person. And then risk control is when we eliminate those eliminate or reduce the risk of a person being exposed to hazard. And then we have HAZOP. HAZOP is a more detailed and complete identification of hazards, include how the hazard can happen, and then the consequences if there is a failure in operating procedure. Later I'll show you an example of HAZOP on one of the equipment. And then plant layout. Plant layout, we includes all the safety consideration and then emergency escape route. So ERP assists companies with various emergency situations. For example, in case of emergency, who is the person to be contacted, what is the procedure when emergency happens, and then how to reduce the risk and what resources to use to minimize the risk. So in this next slide, I'll show you the HAZOP example for separator V100. I'm sorry if I'm looking this way, I'm looking at the slides. Study note, we can see separator, guide workflow, and then deviation node, which in this case, the failure is no flow. And then the possible causes, K100 not working, DC1 not working or shut down. DC1 is the equipment after the separator. And then blockage in piping system, failure of control valve, large leak of piping, error isolation. Possible consequences, no product will produce, destroyed the purity of product, desired flow rate will not achieve. And then we have action required, which is interlock with process shutdown, flow alarm on. So in HAZOP, we can see that in this case, the operating failure is no flow. So there is the expected consequences, what can happen if there is no flow, and then we have the possible causes of that to happen, and then we have action required to overcome that problem, that failure. Okay, so this is our plant layout. It is divided into 2 areas, which is the non-processing area and the processing area. So the non-processing area consists of administrative building, canteen, parking lot, prayer room, medical bay, and then the processing area contains the maintenance building, main warehouse, the quality control lab, and loading unloading bay, and then the processing plant, which the process occurs. And then there is also emergency route. The red and the green one indicates emergency route for our plant. So the red arrow is for the emergency vehicle. For example, in case of emergency, the police or ambulance or fire truck will use that route to go to the destination, to the emergency area, and then the green arrow indicates the emergency escape route for the staff or visitors. For example, in the non-processing area, the people from the staff or the visitors from administrative building will escape to the assembly area 1. So this is our 3D plan layout from the front gate view. And then the front part is the non-processing area, and then at the back is the processing area. I've explained all the details for plan layout in the previous slides. So I guess that's all from us today. Thank you.